Good afternoon, everyone. My name is Gaurav Kaushik, and today I'll be talking to you about how to measure and mitigate bias in healthcare language models, in particular, the kind of large language models that everybody's talking about these days. First, a little bit about myself. In 2019, I co-founded ScienceIO. We're a venture-backed startup based in New York City. We've been building large language models, or LLMs, for healthcare since then. And during that time, we've learned a lot about how to build LLMs specifically for applications with biomedical and clinical data. Before ScienceIO, I worked on data science and product teams in cancer diagnostics, EMR data, and next generation sequencing, which has informed how we think about the design of our systems here. So we tend to see two predominant NLP workflows in biomedicine. The first is fast and accurate information retrieval. Consider that a single patient in an EMR can have hundreds to even thousands of documents or individual events within the system. Clinicians and care teams often struggle to understand the patient timeline. What happens to that patient? Why? Where are they now in their journey? And knowing that timeline is super critical. It's critical for providing the right care, for avoiding adverse events, for being able to understand patterns across populations. There's a lot of need to actually be able to turn that data into something that is hard to navigate, into something that's more useful. So naturally, there's a lot of interest in algorithms that can efficiently retrieve accurate information. The other is structuring variables or essential information in free text. So through things like entity recognition and linking models, we can capture patient attributes to improve downstream analyses. Let's say that you want to do predictive modeling or you want to do survival analysis. How can you get data that's missing from structured fields out of the unstructured records? And in fact, recently a team at Harvard and the Broad used BERT models to find patient vitals missing from structured fields. This paper, which was nicely done, they were able to reduce data missingness by about 31%. And then what they did was train predictive models on that additional data and compared it to data that wasn't NLP enriched. And the predictive models trained on the additional data were better at predicting patient outcomes. So what's nice about this paper is the authors nicely detail how NLP can find missing clinical information and how that can actually improve the kinds of analyses we do on patient populations and patient outcomes. So because NLP systems are being used in the context of clinical decision-making and analytics, it's important to understand that NLP biases can influence clinical outcomes. The behavior of models used to extract clinical information will influence the outcome of analyses using that data. So an unbiased system should capture target variables equally well across all patient populations, all document types, all formats. However, we know that in practice, models have variable performance. Depending on the data they're applied to, they may perform better or worse. So in other words, they have biases. First, a quick definition. Algorithmic bias is what we're talking about today, and that's when an algorithm has systematic and repeatable errors. And in particular, those errors result in unfair outcomes for certain populations. So our whole ethos is that because healthcare NLP systems can influence clinical outcomes through the information that they retrieve or capture, these systems can either mitigate or exacerbate outcome disparities in the healthcare system. So let's take a look at the kind of biases that we're going to encounter and have to manage when we think about building NLP systems. The first is selection bias. Essentially, this occurs when the data used to train a model does not resemble the data it will be used on. A model is trained on a particular kind of document or a particular kind of problems, and then used outside of that context. The second is label bias. In cases where the model is trained on labeled data, biases can be introduced by the annotation strategy that's used, or annotator bias itself. Annotations can be incorrect. There could be poor judgment, human error, people get tired. And you can also see ambiguity in those labels. You may disagree between your annotators how to label the data effectively. So the first two decisions that will impact your model's behavior are the data that you select and the labeling strategy that you use. The next two biases come from training the model. So certain patterns in the data can become over-amplified by the model. Consider a model where it is trained on data where the word met is labeled as a gene 5% of the time. After training, the model could accrue over-amplification bias. And what that means is it might incorrectly infer met, the word, to be a gene at a dramatically higher rate than the label probability in the training data set. So I met you, she met him, might end up getting labeled inappropriately as genes. Next is semantic bias. The input embeddings used in large language models can have associations that are inappropriate for the given task. So, in this example, the word doctor is much more closely associated with man than woman. So there's already a gender bias in terms of how we represent the relationship between these words that is going to be going into the model. And it's important to recognize this. So taken together, all of these biases can result in two kinds of biases that we're particularly focused on when we think about healthcare NLP. The first is demographic bias. That's when you have improper or inappropriate sensitivity to race, to gender, to irrelevant information, which can impair the model's ability to find information relevant to certain individuals. Does this model work better for certain subpopulations versus others? And then there's domain bias. Models will perform differently depending on the context. So within healthcare, this might manifest as reduced accuracy in certain disease settings or in different kinds of clinical information. So how can we evaluate how our models are biased and work to counter unwanted biases? The first thing that comes to mind are benchmarks. Benchmarks are a common way to evaluate large language model performance. If you're not familiar, essentially models are compared on a withheld data set with standardized evaluation metrics. And the goal here is to essentially create an unbiased comparison between multiple models. But these are largely focused on assessing performance. How do we evaluate performance and bias? First, we need to recognize that benchmarks are not perfect. We want to believe they're perfect often. We want to put our faith into them. But in truth, benchmarks require really careful inspection. In particular, I really like this paper from 2021 where Sam Bowman and George Dahl published What Will It Take to Fix Benchmarking in Natural Language Understanding, in which they raised concerns about the most popular general purpose, general language NLP benchmarks. Notably, Bowman led the development of GLUE and SuperGLUE, two of the most comprehensive benchmarks for NLU, and George Dahl is at Google Brain at the time. So Bowman and Dahl expressed that many NLP models were already quickly achieving superhuman performance on those benchmarks. And yet they were failing basic tests in real-world settings. And we're going to get to this in a second. And so they concluded that the tests needed to be much larger and more difficult. A contributing factor was that the benchmarks lacked statistical power. They simply didn't have enough samples to properly evaluate behavior across a full range of real-world applications. And so they encouraged better data set design and collection. Thirdly, the tests need more validation. Benchmarks can have erroneous data, they can have ambiguous examples, and those need to be handled. And finally, and this is where bias comes back into the conversation, benchmarks do not disincentivize bias systems. So what Bowman and Dahl essentially said is they recommend the use of auxiliary bias evaluation metrics to test model biases, in addition to performance on the tests that are created. So let's look at a couple of their critiques. First, let's look at statistical power. Let's consider two models, one of which achieves an average F1 score across a set of tests of 0.95, and another which has an F1 score of 0.9. to verify that the average model, the average F1 score of model 1 is significantly better than the F1 score for model 2, given the constraints here on the slide, we need about 500 test instances to get a distribution and say, yes, the mean of this is actually significantly greater than the mean of the other one. However, as models get better and better, say you're comparing a model that has an F1 score of 0.99 versus one that has a F1 score of 0.98, you need, under the same constraints, over 3,000 test instances to verify that one model is actually performing better than the other. So essentially, as models get better and better, as they achieve superhuman performance, we need larger and larger test sets to evaluate whether that improvement is statistically significant. And relying on a basic comparison on a macro F1 score isn't telling you the whole story of which model is doing better than the other. And then we look at bias, and there's an extra dimension of complexity. So if we look at bias, right? In 2020, a team from University of Washington, UCI, and Microsoft published a paper called Beyond Accuracy, Behavioral Testing of NLP Models with Checklist. And this was a great paper. I encourage everyone to read it. Essentially what they did is they applied behavioral tests to examine state-of-the-art models that were achieving comparable performance on benchmarks, as well as commercial models actually being used. And specifically, they looked in this slide at sentiment analysis. And what they found is that in this example, a BERT model predicted that the I am a blank person statement was negative when that person was Black, atheist, gay, lesbian. And it was positive when that person was straight or Asian. So very clear demographic bias that was being seen in this model, despite seeing excellent scores on benchmarks. Their tests also revealed gender bias in state-of-the-art models and commercial models. So for example, here's an actual case where the model is given the context that a woman is a doctor and a man isn't. So John is not a doctor, Jane is. Prompted, we asked the model, who is a doctor? So the expected result is Jane is the doctor. But 89% of the time, given a traditionally female name and a male name, the model will pick the man over the woman. Below that, we flip it. So now we are asking, who is a secretary? We're changing doctor to secretary. Jane is not a secretary, John is. So the man is the secretary in this case. We expect to see the model say man. Instead, they give the woman's name 60% of the time. So the lesson that comes out of adding behavioral testing in addition to benchmarking is fairly clear. Only by adding those behavioral tests do these biases come to light. And the question we ask ourselves then must be, is performance the only appropriate metric, or is also how these biases are handled and minimized and mitigated in real world use? So this brings us to biomedical benchmarks. And the hard truth is that biomedical and clinical benchmarks that exist out there in the literature suffer from the same drawbacks as those general language benchmarks, but much more severely. So for example, if you look at the NCBI Blue benchmark, the Biomedical Language Understanding Evaluation benchmark, it has 14,000 neurotesting instances, concepts that it is looking at. However, if we look across the entire solution space of where NLP could be applied, let's say we look at the Unified Medical Language System or UMLS ontology, that has over 4 million concepts, which is 2 orders of magnitude difference. So the question then is 14,000 instances enough to test model performance across a broad range of diseases and chemicals? And also, the benchmarks don't use clinical text, path reports, diagnostic reports, or other data types one would typically encounter in the real world. So a lot of our most common benchmarks, our most comprehensive benchmarks, are still rungs below the general purpose ones. And we know those are not perfect. So one of the things that we're particularly interested in at ScienceIO is the task of entity linking. So imagine that you have unstructured records and you want to find, specific drugs or therapeutics within those records. You don't want to just label them and say, yes, this word refers to a drug. You want to know exactly what drug it refers to. So you're going to link it back to an identifier, a unique identifier for that particular drug. So the example I always use is paracetamol, acetaminophen, Tylenol. They all get normalized to the same identifier. That simplifies how we would use that data downstream. One of the most popular test sets for entity linking is the MedMentions dataset from the Chan Zuckerberg Institute. The authors used a 2017 version of the UMLS to annotate PubMed papers. That dataset has not been updated in terms of its vocabulary. They used 2 validators to actually perform validation on the test set. And the scope of that validation was 4 PubMed papers, limited to, I believe, 469 of UMLS entities or concepts. So this reflects essentially what we've seen from our survey of benchmarks across biomedical and clinical NLP, which is that we were not able to find a single benchmark that was sufficiently powered for real-world use, that incorporated a broad range of document types, that was properly validated, and had tests for examining biases that are going to reveal things that a performance metric will not. So it's not doom and gloom. Where do we go from here? And that is a lot of the question that we are asking ourselves and what we're asking our fellows in the community. How do we build a ecosystem to advance domain-specific NLP, in our case, healthcare NLP, clinical NLP? So since 2019, this is the bright side. LLMs have captured the attention, no pun intended, of not just ML researchers, but the general public. Especially now, there's a ton of enthusiasm. And with enthusiasm comes more talent and more resources. So with a zeitgeist like this, it brings opportunities that we didn't have before. Essentially to create a robust healthcare NLP ecosystem that can improve healthcare. So I draw on my experience working in genomics prior to working on NLP for the last several years. A good data and algorithm ecosystem needs 3 basic things. Lots of data that is validated and accessible for training, development, and testing. Tools to keep that data growing and getting better, and evaluating models on that data. So the important thing there is growing and getting better. And tools to examine which data fit the problem you're trying to solve with the model. And which models meet your needs once you have actually trained them. And that will allow for more effective alignment between data, model, use case. So at ScienceIO, as a small startup, we've taken this approach. First, we've continuously scaled up our training data to cover a broad range of use cases in healthcare so that we can focus on generalization. Next, we're working to de-bias test sets with auxiliary tests and data augmentation. So rather than reinventing the wheel across the board, how can we take existing test sets that are out there and augment them with additional data to cover use cases that they don't yet address, and auxiliary tests to look at biases that may be introduced by that data set that can then be mitigated in future updates. And while not discussed in this presentation, we're also investing in data and model cards to make the inputs of models, how they're evaluated, and what data they are more useful for clearer. And finally, while we are doing this within our organization, we plan to publish a benchmark to seed future open and collaborative science. We're looking for partners who want to help build more reliable frameworks for evaluating clinical NLP, biomedical NLP, because it will take a community to do this for the industry. So I have just a couple more summary slides. In the last 4 years, we've essentially learned that industrial scale model evaluation is needed to build models that generalize from an archive paper to real world practice. And the 5 things that we hit upon continuously is having a diverse set of text sources to capture variance across domains, to be able to test that the model works as well in cardiology as it does in oncology, to be able to test that any artifacts from upstream data processing like PDF conversion have minimal impact on the outputs. Then there's the ability to examine performance on specific domains. So if we are going to want to understand which models do better in certain indications or certain types of information, genomic biomarkers versus generic vitals, nephrology versus pulmonology, we're going to need to have these test sets annotated so that you can look at them from different dimensions. We need evaluation of ontologies as well to avoid repetition and noise. So one of the limitations with using ontologies as they are is that they're not always curated to help models essentially disambiguate the text that they are going to be processing. So one example that I use is if you were to go look at the UMLS, I believe in the latest version, and you did a search for concepts or entities related to EGFR, you would find over 1,000. So how does one then take that, make it something that is usable and that a model can learn from and incorporate? So evaluation of ontologies and being able to support interoperability between different NLP systems is also something that is going to be really important. We talked about frameworks for continuous testing on real-world tasks. Essentially, benchmarks being a single snapshot in time will not work for healthcare because healthcare changes. We discover new things, we learn new things, new drugs get developed. So continuous testing on real-world tasks is important. And lastly, there's testing outcomes. So one of the early points that I tried to drive home is that the work that we do in NLP will impact clinical outcomes in some way. So it's very helpful for us to be able to test how the NLP is working, but ultimately the success of healthcare NLP as an industry will be on whether we are improving patient outcomes and addressing and mitigating existing disparities in healthcare. So to summarize, errors and biases in NLP systems can propagate to how the output is used in healthcare if we are not careful. Knowing and countering unwanted or harmful biases is crucial to fostering effective and equitable care. State of the art does not mean unbiased, robust performance in the real world, unfortunately. And high quality and community-driven benchmarks are needed to advance healthcare NLP, is our perspective. Finally, I just want to say thank you for your time. If you are interested in talking more about collaborative efforts, you can reach me at my email address here. If you're interested in learning more about the work that ScienceIO is doing to advance healthcare NLP, I'm always down for a conversation. And finally, a small plug for our platform. You can go check it out at app.science.io. Thank you.